Good day everyone, welcome again to the MathCAD tutorial sessions. Today we're going to be going over lesson number 2, which deals with matrix operations and graphing and MathCAD. We're going to go over the fundamentals of manipulating arrays and operating over arrays and matrices, as well as how to plot, perform 2D plotting, graphing, and obviously 3D plotting as well. So let's continue with start with a presentation. In the first tutorial, the first lesson, we talked about the difference between indexing and range variables, and we can use indexing, we can use range variables to actually index arrays. You can use an integer range variable to create an indexed array, and it's very important that the index is an integer and it has a step over 1. The array must be indexed by the integer range variable so that the correct elements are filled. So for example, if let's say that we enter a range variable I from 0 to 10, we can create an array called time that depends on I, and the index I can be entered with the left square bracket. Remember, that's the difference between text subscript and index subscript. We're actually indexing a variable called time, and we're going to be defining time as I divided by 20, and then we can just define a third variable called x, which is time multiplied by 10, and see what happens. This is what we're going to get out of these operations. So let's do this directly in MathCAD and change them around and see what the difference between all of these are. So let's go to MathCAD. I already have MathCAD open, but remember, you can use the shortcut on the desktop, or you can just use the start menu. And I'm going to create a new MathCAD spreadsheet, or MathCAD scratchpad, whichever way you want to call it. And on the upper left corner, I'm going to say, let's create an index I that goes from 0 to 10. By default, the step over is 1, or the step between elements is 1. Notice that I is a range variable. It's not a vector. It has different values within the range, but it's not a vector. It's not an array. I cannot access different values within I cannot say give me the third value of I. It doesn't understand because I is not a vector. But I can use I to define a vector. And let's define a vector called time, for example, and use the left bracket as a subindex I, and I'm going to define this time array as I divided by 20. Now remember that the green rod underneath time just means that I am trying to double define the variable time that might be used by something else. In this case, because I haven't defined it myself, it means that it's a variable that MathCAD uses for something, but that's just a warning, don't worry about it. And then I'm going to say, well, what is time? And I'm going to just move this down. And notice that the way the time is displayed is completely different as the way that I is displayed. It's displayed in a different box. It has elements from 0 to 10, the indices from 0 to 10, and in column 0, it has a single column 0, I have elements 0, 0.05, 0.1, so on and so forth, all the way to 0.5. Okay, so it's I divided by 20. Now, if I can actually access different values within the time array, and this array is a vector. Give me the third value, 0.15. In the index number 3, the value of time is 0.15. Give me the index 7, I get 0.35. I can actually multiply. I can create another variable called x, which is the multiplication of 10, for example, times, or I had it as 0.1 in the presentation, or 10, simply. 10 times time. And since time is an array, then x will be that by default another array. So x is equal to another array, which is very similar to time, but just with every element multiplied by 10. Okay, so I don't need this for now. Let's just create a range variable I, and an array with that range variable called time. Okay, and now we know the difference between the two. Let's go back to the presentation. The variable I is a range variable, while time and x are one-dimensional arrays or matrices indexed with I. Remember that a one-dimensional array or vector is a matrix that only has one column. Notice that the default initial index or origin for an array is set to 0. Okay, all arrays begin with 0, column 0 to 10 in this case, or row 0 to 10 in this case. The origin may be changed by reassigning a value to a predefined constant. In that case, the variable origin in capital letters, we can redefine it at the beginning of the worksheet, or we can go into the worksheet properties and change the index by 1. So if you feel more comfortable working with arrays whose first index is 1 rather than 0, then you change it this way. So I'm going to go to the MathCAD spreadsheet. Let's move this down a little bit, and I can change the origin in capital letters to 1. Now it gave me all kinds of errors now because I defined the range starting at 0. So I'm going to have to change the range now starting at 1. See, I defined the range starting at 0, and then I try to define an array that starts at index 0, and it didn't let me because my new origin is 1. I'm going to change the index to 1 to 10, the index variable, the range from 1 to 10, and now the range is defined this way from 0.05 to 0.5, and the indices from 1 to 10. Now I can also change, if I didn't specify the origin, notice that the origin by default is 0, and the time 0 is filled with 0 by default. I can change the origin by going to Tools, Worksheet, Options, and I can change this origin from 0 to 1, and it will automatically start the arrays at 1. Let's go back and change that to 0, and let's keep working with our default origin at 0. Okay. We could also define matrices, which is simply a two-dimensional array, or it can even be higher dimensional array, by defining two indices. In this case, let's say that we want to create an array A, a matrix A that has 121 positions, okay, 11 columns and 11 rows. We define a range variable I from 0 to 10 that will actually point to the rows, and J from 0 to 10 that will actually point to the columns. And then let's define A and use the left bracket to index I and J separated by commas, the two indices, and let's just define a function, I squared plus J cubed divided by 4. Alright, and let's see what happens. So as I said, we can create an index from 0 to 10, I, and then we can create an index from 0 to 10. Remember, we use a semicolon to define the index from and to. And let's define a matrix A. Open the left bracket, and the index I and J separated by commas. When we use a comma, we're already automatically saying that we have a rows and we have columns, so we have a two-dimensional array or matrix. And we said that this was going to be I squared plus J cubed, let's use the space bar, select all, divided by 4. Okay, so now I can check what A is. As you can see, it's a two-dimensional array. We can see all 11 rows. We don't see all 11 columns because there's no space, but I can step and scroll within the array to the right or to the left to see all the contents of A. I can use the cursor to move within A. Okay, so, and I can also query specific, since A is an array, I can query specific elements of A. So let's say, give me A element 2, 3, which should be row number 2, column number 3, 7.75, that's 7.75. Give me A 3, 7, that should be row number 3, column number 7, that should be an 88, and indeed we got an 88. Okay, so now we have a matrix. We can also input a matrix, or a vector for that matter, directly by hand, by inserting a matrix from the menu, or just using Ctrl M to insert a matrix. So we can define A, for example, and then use the assignment equal or the definition equal, and use Control M or go to the menu and say Insert Matrix and specify the number of columns and rows, and then enter every single element of the matrix by hand. That's sometimes tedious, but sometimes it's the only way we can enter the value of a matrix if we don't have a definition like this, or if it doesn't come from another source. I'm sorry. So let's say, for example, I can define a matrix A, define or assignment equal, and use Control M. Automatically this window will pop up and say, well, how many you want? Let's say I want 4 rows and 4 columns. Click OK, and I get a matrix with 16 placeholders waiting for me to input values. So I can enter any values here, but I'm going to leave it empty for now, so A is not defined. And I can also enter vectors. Let's say a vector B, Control M. A vector is defined by a number of rows and a single column, and there it is. So I can enter the values for a vector, for instance. Okay, so Control M or Insert Matrix will get you there, after obviously the definition equal. But let's just forget about this for now, and let's just keep operating over the large matrix that we created with 11 by 11 elements. We can also create a matrix by reading a file, and if the file has the proper format, if the file actually contains numbers with the same number of columns and rows, and the data is arranged. By the way, it doesn't have to have the same number of columns than rows. The matrix do not need to be square. We can read this text files using the readPRN command or statement in MathCAD. So we can import files into MathCAD using readPRN. Any extension can be specified. It doesn't have to be txt. If the data file is not located in the same subdirectory where the MathCAD file is, then a full path must be specified. And after the execution of this command, the ordered values on the file name .txt, whatever name that is, file will be imported into A, and we will be ordered in an IJ format. Okay, IJ order fashion. We can also write a matrix that we have created into a file, into a text file, and we do that with writePRN. So we can write PRN as A, or write a file name, whatever the contents of A are. We can use any extension we want. The data file will be written in the same subdirectory as the MathCAD is saved. If not, you need to specify a full path, and then after the execution of these commands, the ordered values of A will be exported into filename.txt. Okay, so let's see. Right now we cannot read any files because we don't have any text files in our subdirectories. First thing we need to do always is just save our MathCAD file. We can click Save directly or Control S, and by default the extension is .xmcd, Extended MathCAD. Okay, this is the extension for newer versions of MathCAD, like version 14, the one we're using. You got to be careful with that because sometimes this is not backward compatible. So let's say that you're working on this version here in school, and then at home you have version 11, for example. You cannot read this XMCD file. You might want to change and save this with a different format. You can save as MathCAD 11 worksheet.mcd directly, and it will be readable by any older version of MathCAD, starting with MathCAD 2000 actually. So I'm going to call this MathCAD 02.xmcd. So I'm going to leave it with the default extension XMCD. And then I'm going to take this matrix A that I created here, and I'm going to write it to file. So I'm going to say write in capital letters PRN, and I'm going to call it matrix A.txt, and I'm going to write A. Alright, so if I go to Windows Explorer, I'm going to see that a file was just recently created, and this matrix A.txt. If I'll double click on it, I see this file. Okay, with all the values. Notice that those values are identical to the values in the matrix, but they are now tab separated values in a file. Okay, I can read those values. Let's say I want to read those values, but I don't want to put them in the variable A because A is already occupied by this. So I'm going to put it in variable B. Read PRN matrix a.txt, and if MathCAD understands it, it will import it automatically, and it will import it into matrix B. So if I say display B, notice, well, B is identical to matrix A, because obviously I imported a file that I wrote as matrix B. So no big deal. Alright, so now you know how to use the write PRN and read PRN, and MathCAD will understand and will be able to import values that are comma separated, space separated, tab separated, any type of delimiter. MathCAD will understand and process. We can operate over matrices, of course, not as difficult as it is in Excel, for example, and MathCAD is very simple. If I have two matrices, I can add them just by using the plus sign. If the matrices are addable, meaning that the two have the same dimensions, I can add them. If we can subtract the two, if the dimensions correspond to each other, we can subtract. We can multiply by a scalar. We can actually extract a specific column of a matrix by using the Ctrl+6 operator. It will tab into a specific column of a matrix. Let's see how that works. Now I have two matrices, A and B. They happen to be identical because I wrote A into file and then I read A from file and put it into B. Now I'm going to say that B is now 3 times B. Okay, so I'm going to be multiplying B by 3 times and storing the solution into B again. So that's multiplying by a scalar. It's giving me a warning because I am redefining B. But it doesn't matter, that's exactly what I wanted to do. Now I have the matrix B. Notice that it's the same thing as A, but multiplied by 3. Every element is multiplied by 3. That's called multiplying by a scalar. Now A and B have exactly the same dimensions. They're 11 by 11. They have rows from 0 to 10, columns from 0 to 10. So I have 11 rows and 11 columns. I can say C is A plus B. Right? So here's C, A plus B. I can say, for example, give me the vector V will be defined as column number 3 of A. So I'm going to say A, Ctrl+6 to access a specific column, Ctrl+6, and then I'm going to say column number 3. So vector V should be retrieved as this vector right here, column number 3. Let's see if that's correct. So V is equal to exactly column number 3, 6.75, 7, 7.75, so on and so forth. So that's multiplying by a scalar, adding or subtracting, and extracting a specific column of a matrix. I can also transpose a matrix very easily by saying, well, transpose a matrix that is not to the power of T. Be careful with that. It's Ctrl+1 will automatically call the transpose operation. We can multiply two matrices, remember, only when the indices of the two matrices or the dimensions of the two matrices allow for the two matrices to be multiplied. Remember, the number of columns of the first matrix has to match the number of rows of the second matrix. Otherwise, they cannot be multiplied by each other. We can calculate the determinant of a matrix by simply using the shift forward slash or backward slash, vertical brackets, and I can calculate the inverse of a matrix by just simply taking it to the power of -1. So let's see. Now A and B have exactly the same dimensions because I created B from A. So I can say that D is A times B. That's perfectly multipliable. So matrix D is a multiplication of A times B. I can calculate the transpose. I can say E is the transpose of A. A, not to the power of T, but Ctrl+1 will access the transpose operation. And if I click E, it will be identical to the transpose of A. Notice that the first row of A, 0, 0.25, 1, 2.25, 4, 6.25, is now the first row of E. 0, 0.25, 1, 2.25, 4, 6. So all the rows of A are now taking all the columns of E, and vice versa. I can take the determinant of a matrix. I can say, well, give me the determinant. I'm going to call it, I don't know, D, lowercase d. The determinant is shift backward slash. That's the vertical bars, of A. What is the determinant of D? 0. That means that the matrix is singular. Okay, so be careful with that. That means that that matrix doesn't have an inverse. So if I try to say F is the inverse of A to the power of -1 directly, it will give me an error. See, this matrix is singular. It cannot find the inverse, and that was given by the determinant. Can we calculate the determinant of another one of these matrices? Let's say B. Well, if A was singular, then B is singular, because B is simply 3 times A. It's also 0. Is C singular? Definitely, because C is A times B, which is the summation of 2 singular matrices. Let's see D, for example. That's also singular, because it's the multiplication of 2 singular matrices. How about E? E is also singular. So singular matrix yields singular matrix all over the place. So we'll exercise this inverse a little bit more when we get to solve systems of equations in a few seconds. There's a few more, or actually there's many more. There are many more functions for matrix operations that we can use. Some of them, some important ones, are matrix. For example, you can specify to create a matrix. I'm going to say A is defined as matrix of number of rows, number of columns, and a function. I can use a specific function of x and y, for example, to define a matrix this way. I can create an identity matrix with dimension C. Give me a 5 by 5 dimension identity matrix, and you say, well, I is equal to identity 5, meaning that all the elements will be 0 except the diagonal, that will be 1. I can actually extract a submatrix out of a matrix. If I have a matrix called A, I can extract the rows from row 1 to row 2 and the columns from column 1 to column 2 consecutive, and I can extract a submatrix, rectangular or square, out of a matrix. I can augment A and B, for example, given two matrices A and B with the same exact number of rows. I can augment the two, meaning that B will be augmented or will be pasted to the right of A, okay, to create a new matrix C. So you can say C is augment A plus B. Or I can stack them. I can put B underneath A. As long as B has the same number of columns as A, I can stack the two into a new matrix called C. So those are some examples of use of matrix functions. Some other examples include sorting, which only applies for one-dimensional arrays. So if I have a vector V, I can sort the vector, okay, in ascending order. I can reverse it, so it will be in descending order. I can column sort a matrix. If I have a matrix A, I can specify the column number I want to sort by. So I have a matrix, and I say I want to sort the entire matrix referenced by sorting column number 3, for example. And then it will sort column number 3, and it will accommodate the rest of the elements according to that sorting sequence. And it can do so by row also. I can specify a specific row, and it will sort that row, and then will arrange the rest of the elements according to the sorting sequence that it used. So some of these functions you will get to use, so some of the functions you can just simply exercise in the MathCAD pad, and just to see how they work. Now, the most important feature or aspect about being able to use and manipulate and operate over matrices is that, as you know, as we've gone over in previous tutorials, matrices can be illustrating a linear system of equations, okay, that can be derived from the application of a specific science or engineering problem in many different fields. So we have a system of equations that is illustrated by a matrix, and the right hand side of the system of equations, or independent terms, are illustrated by a vector B. The vector x is the vector of unknowns. It's what we want to determine out of that system of simultaneous equations. Remember that we can find the solution of a system of equations as x equal the inverse of A times B. We have another function in MathCAD called the LSolve function. We can say linear solve matrix A, comma vector B, and as long as the dimensions are consistent, meaning that B is a vector that has the same number of rows as the square matrix A, and that A is non-singular, then we'll get a solution X. So let's test this. Let's enter a matrix, a 5 by 5 matrix by hand with these values, and this is illustrating a system of equations where we have 5 unknowns. Those 5 unknowns can be I don't know, pressures at different points. It can be different flow rates at different points. It can be different temperatures at different points. They can signify different voltages at different nodes in a circuit, or intensities or currents at different points in a circuit. Then we have a right-hand side vector b, which is the right-hand side of every equation. So let's say that these are temperatures, or these system of equations is a system of equations for 5 different temperatures. It will be -1 times temperature 1, 1 times temperature 2, 2 times temperature 3, 3 times temperature 4, and so on. And those temperatures will be here on an x vector, okay, the vector of unknowns, and it will be equal to -1. So this is equation 1 and the right-hand side of equation 1, equation 2, the right-hand side of equation 2, equation 3. Every row is a different equation in the system. So let's see. Let's enter these quantities, -1, 1, 2, 3, 1. So let's start a new page, and let's say A is Control M to enter a matrix by hand, 5 rows, 5 columns. Okay, we got 5 rows and 5 columns. -1, 1, 2, 3, 1. That's the first equation. Second equation, 0, 2, 1, 2, 1. 0, 2, 1, 2, 1. Third equation, 1 minus 1 minus 1, 2, 3. 1 minus 1 minus 1, 2, 3. Fourth equation, -3, 1, 1, 2, 2. -3, 1, 1, 2, 2. And the last equation, 1, 0, 0, 2, 3. 1, 0, 0, 2, 3. Let's also enter the right-hand side vector of independent terms. B is -1, 2, 3, 2, -2. It's a vector, Control M, 5 by 1. It's -1, 2, 3, 2, -2. Is that right? Yes. Okay. So as I said, we have 2 ways of determining the solution of the system of equations. Remember that this is a system of equations because it has 5 equations for 5 unknowns. Every equation has a right hand side, so we have -1x1, 1x2, 2x3, 3x4, 1x5 is equal to -1. That's equation 1. Whatever that equation means, whatever those x's are, that's a system of linear equations. Can we solve the system? Well, let's look at the determinant of matrix A. Is -37. That means that A is non-singular. Okay, so that means that A has an inverse. We can determine the inverse of A. We can say, give me the inverse of A, and there it is. How do we know that that's indeed the inverse of A? Let's just put it into another matrix, and we're going to call it I don't know, C is the inverse of A. So C being the inverse of A looks like this, and let's see if it's indeed the inverse. If I multiply the inverse of a matrix, C, which is supposedly the inverse of these matrix, is also a 5 by 5, and I'm going to multiply it by A, I should get the identity matrix. Let's see. 1, 1, 1, 1, and 1 in the diagonal, and everywhere else I get a 0. The reason why I don't get a 0 here is it's very close to 0. There's just numerical noise. -1 times 10 to the -15. That's very, very small number. You can say 0. So let's solve the system of equations. The first way of solving a system of equations is, let's say x1. I'm going to call it unknown. X is equal to a to the power -1 times b. Now we know that a has an inverse because it's non-singular, and we know that b has the same number of rows as a has columns, so that means that this is multipliable. And how much is x? That is a solution, 1.5411784. The other way of solving system of equations, LSolve, using the function LSolve, a comma b, and let's say how much is x, and it's identical. It's exactly the same thing. Now what is the difference between the two? Well, this one is much slower than this one. We didn't notice it because this is just a 5 by 5 system. But if we had a 100 by 100 system, this will take a long time because it needs to calculate the inverse, and the process of calculating the inverse is a lot slower than the process of solving the equation system directly, like this. So if you had a large system, this not only will be faster, but it will tend to be more accurate because there will be a lot less numerical noise. This operation will carry a lot of numerical noise because calculating the inverse of a matrix requires a lot of consecutive operations that will carry this error, propagate this error forward. So you will see a lot of noise, especially obviously on the decimal places and the far decimal places. So it's a lot safer and faster to use the LSolve as long as the system is solvable. And this is what we found. Okay, in the system solution of the system of equations, we found identical solutions. We didn't notice a difference in speed because obviously the system of equations is very small. Now let's move directly into plotting. How can we graph with MathCAD? Well, we can graph functions, we can graph vectors or indices, and we can also do so with matrices in 3D, and we can do so with functions in 3D. So we have two ways of plotting, either using index variables, or using functions. Okay, the difference between the two is essentially no difference. When would you use one or the other? Well, if what you have available is an index variable, then you plot the index variable. If what you have available is a function, an explicit function, then what you use is a function. So let's plot with index variables, for example. Let's say that we create a range variable from 0 to 100, I from 0 to 100, then we create an array called time that is defined, it's an array indexed with I, that is defined as I divided by 100 to the square power. Then from the insert menu we'll select graph, and then we select XY, and on the X axis we'll enter I, and on the Y axis we'll enter time I. This is what we'll see. Okay, we'll see just a quadratic function from index 0 to index 100, and I going from 0 to 1 because time is from 0 to 1 square, which is 1. So let's see how that works. Let me create another page break here because we're moving from matrices to plotting indices now. We'll create a range variable I from 0 semicolon 100. By default the step is 1. Now I'm going to create a vector called time, indexed by I with the left bracket index, defined as I divided by 100, use the space bar to select all, to the power of 2. And now I am going to say insert graph and XY plot. So I'm going to enter I. Let's make this a little bit bigger. I'm going to enter I on the x-axis, and on the placeholder on the y-axis I'm going to enter time I, and there's my plot. Okay. By the way, MathCAD plotting is also parametric, so if I change the exponent, for example, to 3, that will change. I'm going to change it to 7, so there's a steeper difference, and notice that the graph changed. I'm going to change it to 1, I get a straight line. Change it to 2, get a quadratic function. Okay, so this is plotting with indices. Okay, index goes on the x-axis, vector goes on the y-axis. I can also plot with functions. If I define a function explicitly, like the way we define functions on lesson number 1, y of x is equal to x squared, and then define x with a range between 0 and 1, for example, and steps of 0.01. This is, I have a function that is called y of x equal to x squared. This can be a function of temperatures, a function of space, and the space goes from 0 to 1, and this is 1 meter or whatever. And I want to see the plot at steps of 0.01. Notice that this is a range variable, x, but it's not indexed to y. It's not an index to y. Y is just a function of x. And again, we're going to, from the insert menu, we're going to insert a graph. And the x-axis we enter x, on the y-axis we enter y of x, and we should see a quadratic plot. Okay, so this is plotting using functions. So I'm going to define a function y of x. I don't have to define the range variable x before defining the function because the function is just an independent definition, and it's x squared. Right? Now I need to plot this function, x or y as a function of x. But I want x to go from, if I don't define x, and if I say insert graph x, y, I'm going to make this a little bit bigger, like this, and I'm going to say enter y as a function of x, and x on the x-axis is going to plot something for me depending on the value of x. But notice that it plots something really strange, and what it would do is just pick the default value of x that it had. And by the way, we use x to define this vector, so it's actually plotting y as a function of x, x being minus 1.541, 1.784, and so on and so forth. So this is not an error. It actually picked the last value of x it had. Let's define x now as 0, 0.01, semicolon 1. And now I'll plot a quadratic function between 0 and 1 in small steps. See? I can change this exponent to 8, and it will change the function. The shape of the function is a lot steeper. I can change this to, I don't know, the square root of x, and I will just change it from convex to concave, or go back to whatever, x squared. And there's my function that looks identical to the one above. Alright, so let's just insert another page break here. Now, let's try this with a more complicated example. Let's just use this compounded trigonometric function, sine of pi times time plus the cosine of 2 pi times time. And let's just plot this from 0 to 5 seconds. And let's just use either an index variable type of plotting or a function type of plotting. So let's start with a function. In this case, it's a lot simpler to do this with functions, and what we're going to do is see what this function does between 0 and 5 seconds. Okay? So we'll go to MathCAD. Let's define a function y of t. This can be the vibration of a string as a function of time, maybe. I don't know. Sine of pi times t plus the cosine of 2 times pi. Remember, pi is entered as p control G. Pi being the equivalent of p in the Greek alphabet to the p in the Latin alphabet, times t. Alright? So, let's plot this using t from 0, 0,05 maybe, to 5. So, let's say we have 100 steps between 0 and 5. So we can change this value to whatever we want, but that should be enough resolution to let us see this plot smoothly. And by that I mean the following. So I'm going to plot y as a function of t, and this is what I'm going to see for the first 5 seconds. Okay, this is maybe the location of a subatomic particle in a force field. Whatever it is, it's just defined by this particular solution, by this particular equation. Now, I wanted to see the solution between 0 and 5 seconds, and I use a resolution of 0.05. I could change this resolution, for example, to 0.5 seconds and only have 10 steps between 0 and 5, and I will see something that is not really smooth. Okay, so in order to avoid those tight corners, I just use a larger resolution. Now, how would I do that? Using index variables. I want to see the same plot and create the same exact plot using index variables. The first thing I need to do is create the index, I. It's got to be integer. I'm going to use 100 steps from 0 to 100. Now I'm going to define the time. The time as a function of I is I divided by 20. Okay, that will take me from 0 to 100 instead of, or from 0 to 5 instead of 0 to 100. So t, if I plot t, or if I display t, will go from 0 to 5 seconds and steps of 0.05. It's exactly the same as the definition we made above, but now we have an array of index I. And now let's create y, which is also indexed by I, and that will be the sine of pi times t sub I plus the cosine of 2 pi times t sub I, sub being the left bracket. And that is exactly the same function as this function up here, but now it's an index value, is an array rather than an explicit function. So now I can plot this. I can plot t of I on the x-axis, and I can plot y of I on the y-axis, and there it is. It's very smooth. Okay, I can also use I on the x-axis, but notice the x-axis will go from 0 to 100 to the number of indices we have. So let's just change that to ti. If I double click on the plot, I can access the different formatting configuration. I can change the traces, for example. The first trace is red. I'm only doing one trace per plot. I can actually plot different functions within the same plot by simply separating by commas, and the dependency separated by commas. It's very easy. We're going to get to do that in future lessons. I can change the color to maybe, let's say, blue. Apply. I got a blue plot now. Let's change it back to red. Apply. I can change the line to maybe dots instead of lines, or maybe dash lines, or dot dash, whichever way I want. And I can change the weight, make it a thicker line. A lot of configuration options. Numbering format, I can add grid lines. I can change the axis, make it more dense than the indices in the axis, and many things I can actually configure within the formatting configuration of the plot. So let's enter a page break here and go to the next exercise. So that's the difference between plotting in 2D using functions explicitly or using index arrays. Okay, and this is what we got at the end of the day. Now notice that I use in this example only 50 steps to go from 0 to 5 seconds, so it's not as smooth as the 100 steps that I use in the exercise in MathCAD. Now let's move into 3D graphing. 3D plotting in MathCAD is very straightforward. We don't have to create multiple columns or multiple rows of something and then multiple series like it happens in Excel. 3D plotting in MathCAD is just a natural extension of 2D plotting. All we have to do is insert a 3D plot, which can be in the form of a surface plot or a contour plot. And then we have a lot of configuration options that we can play with. Configurations such as the angle, the height, the elevation, the colors, the wireframe, the lines, and so on and so forth. Now by creating, we can do this two ways. We can do it the same way we did in 2D, either by index arrays or by functions. If we have an index array, in this case a matrix, you need a matrix to have a 3D plot. If you have a matrix, you can plot it directly. Or if you have an array, a matrix, you can plot it directly. Or if you have a function, defined function of two variables, function of x and y, you can plot it directly by inserting a 3D plot. So for example, let's start by plotting a matrix, and for that we are going to use a predefined text file that I've included with this presentation called MathCAD02.txt. That MathCAD02.txt file has 21 by 21 elements. It's a 441 element matrix, and it's got the elements of a matrix that came from, who knows, it came from an experiment, it came from some measurements, measurement lab, or some mathematical function that's defined this particular shape. Okay, and we are going to import that into a matrix using the readPRN statement in MathCAD. So we're going to import the text file into a matrix, and then we're going to plot the matrix A. I'm going to try to make it look like this. Okay, so that file will be located with this presentation as MathCAD02.txt. Notice it's just tab separated values, many values, so 20 by 20 or 21 by 21, many values. We're going to grab those values, store them in a matrix, and then try to plot them, because a plot says a lot more than obviously this table. We cannot see any pattern, or maybe not imagine specific pattern out of this table, but if we plot it, we'll see it directly. Okay, so it's called MathCAD02.txt, and it's located in the same directory as this MathCAD pad, this MathCAD file. So what I'm going to do is A is read PRN of MathCAD02.txt. I read it correctly, it didn't give me any errors. I can actually display it. It's too large to display, but notice I can scroll to the right, and it's got all the way to 20. From 0 to 20, that's 21 columns, and from 0 to 20, that's 21 rows. And what I want to do is display this matrix. Okay, so the matrix A can be displayed by simply going to the insert menu, graph, surface plot. Another way of plotting 3D will be to 3D scatter plot or a contour plot, but I want a surface plot. I want this nice looking in 3D, and in the placeholder I'm going to simply say A, and there's my plot. Okay, I'm going to move this over here to the middle. Let's make it a little bit bigger, and by double clicking on it, we're going to start changing the appearance of these. I'm going to go to the appearance tab and change the fill options to fill surfaces, and change this to color map. Hit apply. I have a color map now. Okay, high means red, low means blue, or blue means low, red means high. Let's eliminate the lines, no wireframe. Okay, it's only this. There's a lot more things to this configuration. We can change the lining, we can actually box this out, we can change the X and Y axis and change the values on the X and Y axis. We can add titles and backplanes and a lot of special, and the lining I can enable lighting, and you'll see shadows. And let's just disable this for now and click OK. So I can actually click inside, and with the left button of the mouse, and by dragging I can rotate. I can use the scroller of the mouse to zoom out or zoom in. Okay, and by right clicking I have an access to specific formatting. I can add fog or lining, so I can see this with some shadows and some fog. Let me eliminate this. That's right clicking, and there it is. Well, that's what we imported from that text file that we imported into a matrix, and now in this plot it actually makes a lot more sense, or at least we can see a pattern. If this is I don't know, telling us what the charge of a particle is at a specific location in space, then this will tell me a lot more than that table. Okay, the second way of plotting in 3D, oh, by the way, before I change that, I can actually change this surface plot. This is called a surface plot because we see the 3D distribution of these. I can double click and go to general and change the surface plot to contour plot, which is nothing but seeing this from the top. So if I click OK, I am seeing exactly the same plot from the top. So if I double click, go to appearance, fill contours, apply. Actually, let's just no lines, and I can change this to have a lot more contours. Fill contours, contour lines. There's a way of changing the number of contours so this looks a lot more smooth. And but usually the best way of looking at, unless you're interested in the specific contours and where the value is high in space and where the value is low in space, for plotting this in a report, usually it's more telling to see this in 3D using the surface plot. Back to appearance, fill contours, no lines. Oops. Surface plot, back to appearance, fill contours, no no lines, apply. Alright. So we can also do this inserting 3D graphs by using a function. So we define a function from x and y. We can even range the variables x and y to specific locations, or MathCAD will actually range them by default for us. And let's just say z is a function, explicit function of x and y. It's got to be a function of two variables, x squared over 2 minus y squared over 4. This is the equation for a parabolic hyperboloid that's center at 0, 0, and that opens in the y direction. So it's also called a horizontal. So we can create this in MathCAD directly. Z of x and y is equal to x squared over 2 minus y squared over 4. Parabolic hyperboloid, or hyperbolic paraboloid, I'm sorry, it's the other way around. And then insert graph, surface plot, and just type Z in the placeholder, and there's the hyperbolic paraboloid. And then I can change the appearance to add contours and no lines, apply, and OK. And then I can look at this at different angles, different elevations, different zoom, and here it is. Okay, so this is 3D plotting in MathCAD, and as you can see, it's very, very simple. Either plot a matrix or plot a function of two variables. So this is it for today, and we looked at different aspects of MathCAD, a little bit more advanced than lesson number 1. We looked at the operation with matrices, solution of systems of equations, and we looked at how to plot 2D and 3D plots. So obviously we'll get back to this plotting and more advanced features of MathCAD when we get to them in future future tutorials, lessons. So thank you very much, and I'll see you next time.